Hello, we're going to talk about rules for assigning oxidation numbers. Oxidation numbers are important. They're used for bookkeeping purposes in chemistry to help us see how atoms are changing when they undergo oxidation reduction. The oxidation numbers can have positive or negative values. They don't necessarily have to be integers. They can be fractional. And an important thing to keep in mind is that they may or may not have any real physical significance. If it's an ion, yes. If it's a covalent molecule, these oxidation numbers are fictitious, if you will. They're just helping us to show how change is taking place. The first rule is that the oxidation number of an element in its free or uncombined state is 0. For example, if you've got metallic aluminum or metallic zinc, they're solids, their oxidation numbers are 0. And this is also true for any of the diatomic elements that are found in nature. For molecular hydrogen or oxygen or nitrogen, for any of the halogens, their oxidation number is equal to 0. Phosphorus exists as two allotropes, P4 and P5. In that case, the oxidation number on P4, the phosphorus in P4 or in P5 is 0. And sulfur as a molecular species comes as S8. And so the oxidation number on sulfur in S8 would be 0. So the oxidation number of an element by itself with no charge is 0. Now if we take an atom and make an ion out of it, a monatomic ion where it has only one atom, the oxidation number is equal to the charge. So if we look at the sodium +1 ion, it's going to have a +1 oxidation state or oxidation number. Sulfide, S2-, will have an oxidation number assigned to it, be a -2. Monatomic ions, the oxidation number is the same as the charge. We talk about neutral compounds. In rule number 3, the oxidation numbers all have to add up to 0. The sum of the oxidation numbers in a neutral compound is 0. So if we look at water, H2O, we've got two hydrogens, each worth +1. We've got oxygen that has an oxidation number of -2. So if we add those all up, we have the sum of the oxidation numbers equals 0, and the sum of the oxidation numbers in a neutral compound has to be 0. Rule number 4, we're looking at polyatomic ions. The sum of the oxidation numbers in a polyatomic ion has to equal the charge, the overall charge on the ion. So if we look at sulfate, which is SO42-, the sulfur has a +6 oxidation number. Each oxygen has a -2. So 4 times -2 is -8. So if I add +6 to -8, I wind up with -2 as what the sum of the oxidation numbers is, and that in fact is the charge on that sulfate ion. Rule number 5. The oxidation number of an alkali metal in a compound is +1. So things like sodium, lithium, potassium, rubidium, and cesium, when we put them in a compound, their oxidation number is always going to be +1. The oxidation number of an alkaline earth metal, that group 2A, calcium, barium, strontium, etc., those are always +2. So that's rule number 5, taking care of those. Rule number 6, the oxidation number of oxygen in a compound, and we're not talking about O2 or O3, we're not talking about those, we're talking about a compound that's combined with another element, is usually -2. There are a few exceptions in peroxides and superoxides, and we'll see one of those exceptions a little bit later, or actually a couple of those exceptions. Rule number 7. The oxidation state of hydrogen in a compound is usually +1. It's +1 if it's combined with a nonmetal. If it's combined with a metal, it's going to be -1. And so +1 with a nonmetal is It's minus 1 when it's combined with a metal to make a binary metal hydride. Rule number 8. The oxidation number of fluorine is always minus 1. And we're talking about fluorine being in a compound with something, not F2. In F2, the oxidation number of the fluorine, each fluorine is 0. But when it's combined with something else, that oxidation number is always going to be minus 1. The other halogens typically also are minus 1, but not always. But fluorine is always minus 1. So you may want to pause the video if you like here and go back and review these rules before we go forward. So let's look at these example problems. And for the first set, let's calculate the oxidation number of nitrogen in the following compounds or species. So NO2 minus, this is the nitrite ion. And the rule we're going to apply is rule number 4 up above. And that the sum of the oxidation numbers has to equal the charge on a polyatomic ion. So what do we know here? Or suspect that we know? We'll look at rule number 6 that says the oxidation of oxygen almost always is minus 2. And that's going to be the case most of the times, and certainly here. So each oxygen is minus 2. And I've got 2 of them. So that gives me minus 4. And I'm trying to figure out what nitrogen is so that when I add it up, it gives me an overall charge or sum of oxidation numbers equals minus 1. So in this instance, the nitrogen has to have an oxidation number of plus 3. Plus 3 minus 4 gives me my minus 1 overall charge. That's for nitrite. Into H2. Whenever we're doing a compound, this is a neutral compound, it has no charge, we try to find out something to hang our hat on, something that we know for sure. And so whenever if we look back at rule number 7, the oxidation number of hydrogen in a compound with nonmetals is plus 1. How many hydrogens do I have? I have 2 of them. So 2 times plus 1 is plus 2. Now I need to find out what the 2 nitrogens are that would give me an overall summation of oxidation numbers equals to 0, which is equal to the charge of a neutral compound. So if the hydrogens all add up to plus 2, the nitrogens all have to add up to minus 2. And since I've got 2 of them, here the oxidation number on each nitrogen is minus 1. Into O2. We figure out what is that we know for sure. We know the oxygen almost always is minus 2. So what must the nitrogen be? The sum of the nitrogens has to be plus 2. So that the sum of the oxidation numbers equals to 0. So if all the nitrogens have to add up to plus 2, each individual nitrogen has to be plus 1. So the oxidation number of nitrogen in N2O is plus 1. N2O4, dinitrogen tetroxide. Oxygen almost always is minus 2. I've got 4 of them. So altogether, they add up to minus 8. The sum of the oxidation numbers has to equal 0 in a neutral compound, which this is. So all the nitrogens have to add up to plus 8. I've got 2 of them. So what is each nitrogen going to be? 8 divided by 2 is 4. So the oxidation number on the nitrogen in N2O4 is plus 4. HNO3, this nitric acid. What do we know? Each oxygen is minus 2, and the hydrogen is plus 1. So how many oxygens do I have? I've got 3 of them, so they all add up to minus 6. I've still got my plus 1 from my hydrogen, excuse me. So how can I get all of that to equal 0? and estimate the nitrogen equal to plus 5. So the oxidation number of nitrogen in nitric acid in HNO3 is plus 5. Ca3N2, calcium nitride. It's actually an ionic species. We got a metal plus a nonmetal. So we're going to resort back to rule number 5 that calcium's a group 2 alkali earth metal. So it has a charge of plus 2, which means it's got an oxidation number of plus 2 on each individual calcium. How many calciums do I have? I've got 3 of them. So in all, that adds up to plus 6. The nitrogens, they've got to add up in all to minus 6 so they can get an overall charge of 0. So this minus 6 comes from 2 nitrogens. So what is each nitrogen worth in terms of oxidation number? Minus 3. N2, diatomic molecular oxygen. Go back to rule number 1. Elements in their standard state, elements by themselves in their free uncombined state, the oxidation number on each atom is 0. N3 minus, the azide ion, something that we haven't encountered yet. I've got 3 nitrogens. It's a polyatomic ion. The sum of the charges has to add up to minus 1. So I've got 3 nitrogens, each equal, when you add them all up, it has to equal minus 1. So what's each nitrogen going to be? Minus 1/3. Minus 1/3. No, there's no charge on each individual nitrogen. Yes, there's a charge on the species as a whole. It's been given an extra electron. But the oxidation numbers on each individual nitrogen here is minus 1/3. No real physical significance, but it's useful in bookkeeping purposes when we look at reactions. So we've done problem number 1. Let's look at problem number 2. In which case we're going to calculate the oxidation number on oxygen in each of the following compounds. So O2, diatomic molecular oxygen. It's an element in its free, uncombined state. Rule number 1 says that oxidation number on each oxygen is 0. Water, which we actually talked about up above. If we look at our rules, hydrogen with the nonmetal is plus 1. I have 2 of them. They all add up to plus 2. So what does oxygen have to be to give us an overall charge of 0? That's right. The oxidation number on oxygen here is minus 2. It's not a charge, it's the oxidation number. So let's look at its first cousin in terms of being a compound, H2O2, hydrogen peroxide. And here's where one of the exceptions come in. If you look at rule number 6, it says that oxygen almost always is minus 2, except when it's in something like a peroxide or a superoxide. So what do we know for sure? We know the hydrogen, each hydrogen is plus 1. The hydrogens are plus 1. I've got 2 of them, so they add up to plus 2. The oxygens altogether have to add up to minus 2 to give me an overall charge of 0. So I've got 2 oxygens. They have to add up to minus 2. What does the oxidation number on each oxygen? Minus 1. 2 times minus 1 is minus 2. Add that to plus 2 gives me my overall charge of 0, which a neutral compound is. The last example, OF2, oxygen difluoride. Fluoride, fluorine, when we put it in a compound, it's always going to have an oxidation number of minus 1. How many fluorines do I have? I've got 2 of them. 2 times minus 1 is minus 2. So what does oxygen have to be to get the overall sum of the charges to be 0? Got minus 2 from the fluorine, and now I've got 2 oxygens. What's the charge on each oxygen, or the oxidation number rather? Because there's no charge. the oxidation number on oxygen in OF2 is +1. Thanks for listening. If you need to go back and review the video, certainly get out your book and read the sections that pertain to this.